Hello students, welcome to MEMONEET. So this is Aprajita, your chemistry SME, and this is our second lecture for classification of elements and periodicity in properties. So today we will be seeing how the different trends in periodic properties are there in our periodic table, right? Like how atomic radius will vary from left to right in the period or down the group. Then we'll talk about electronegativity, ionization enthalpy, and all of that. So in the last lecture, we studied about the periodic table, how periodic table looks like, what are the electronic configurations of the elements. Then we studied the different blocks, that is S, P, D, F block, right? So today we will be talking about the classification. All right. So let us move ahead. So first of all, we need to understand atomic radius. So atomic radius basically deals with the size of atom, right? Size of atom. So if we are talking about size of atom, how we can measure? So you know that atoms are really very small, so it's a lot possible, or it is not easy to measure their size. So atomic radius is represented in different ways. Okay, so covalent radius. So we all know about what are covalent compounds, right? Where sharing of electron takes place between two atoms. So covalent radius means 1/2 the distance between the nuclei of two covalently bonded atoms of the same element, okay, in the molecule. So generally we use this for the non-metals, because non-metals, we know that in the case of non-metals, we usually have covalent bonding, right? So let's say two non-metals are bonded with each other, so sharing of electron takes place like this. So if we have two atoms of the same element, so it will be like this. So these are the nucleus, okay. So we will say ki covalent radius will be, this is your bond length, okay, distance between the nuclei of two atoms, this is the bond length. If I do its half, okay, so then this much will be our covalent radius, okay, half of the bond length we can say. So this is how we represent the atomic radius of non-metal. So these things I am telling you so that you should know how the atomic radius is measured. Alright, then if we talk about metallic radius, so metallic radius we'll be talking in case of the metals. So it is half of the internuclear distance present between two adjacent metal ions in the metal lattice. So basically we know that in the metals, in the case of metals, you have these kernels, means the positive charges, and sea of electrons is there. So if I am talking about metallic radius, it will be 1/2 of the internuclear distance present between two adjacent metal lines. So these are two metal lines, all right. So in that case, this is your internuclear distance. And if we do the half of internuclear distance, that will become your metallic radius, this one, okay. So if we are talking about metallic radius, it is present between two metal ions, two metal atoms. Then van der Waals radius is also something you will have to study. So in the case of van der Waals radius, it is actually half of the internuclear distance between nuclei of two non-bonded isolated atoms, okay, or you can say adjacent atoms belonging to neighboring molecule, like this you can see. So these are the two bonded atoms, all right, they are isolated, they are molecules, they are isolated. So in that case, this is the internuclear distance, and if we do 1/2, so it becomes the van der Waals radii, and usually we use it for the case of inert gases, okay. So it will be the internuclear distance present between atoms of inert gas and solid state. So in solid state, then we find it out. Okay, so these are the different types of radii. So now if I talk about the trend. So firstly, we will study two trends, period and group. So if I am saying ki if we move left to right, now what is this Z effective? Z effective means the effective nuclear charge. Now what is effective nuclear charge? So you know that nucleus is the one that is holding the electrons tightly, no? So what happens is that when we are moving left to right in the periodic table, so electrons are getting added to the same shell. So nuclear charge is increasing, but since electrons are getting added to the same shell, same energy level is there, so nuclear charge increases, means the hold of nucleus on the electrons increases, means effective nuclear charge is more. So if effective nuclear charge is more, what will happen? The nucleus is going to attract the electrons more towards itself, and that is why the atomic size would decrease. So that is what happens in the period. Like if I am talking about sodium, it's 281, then 282, 283, 284. Then phosphorus is 285, sulfur is 286, and 287 for chlorine. We are not talking about the noble gases here, okay? So in this trend, the outermost electrons are pulled closer, because you can see the outermost electrons are getting added to the same shell. Alright, so because of increase in nuclear charge, electrons are pulled strongly to the nucleus and the size decreases. That's why we are saying that atomic radius is inversely proportional to the Z effective. Z effective means the effective nuclear charge. Okay, and you should know that the radius of the noble gases is more than all of these, because in the case we measure van der Waals radius, and van der Waals radii are always more, and moreover in these cases electron repulsion is there, because noble gases are fully filled. All right, they are fully filled shells. So this trend is applicable to group number 17 only. We don't consider the noble gases. Okay, so see, this is what for second period we have written, and for third period. So try to understand that atomic size decreases generally when we move left to right in the period. Okay, so these are general trends. Exceptions can always be there. Keep that in mind. Now let us talk about the group. Now in the case of group, we will be seeing the number of shells. So in last lecture we have studied that when we are moving down the group, what happens is the number of shells increases, like this: 2281, then 2881, like this. So what is happening? The number of shells are increasing when we are moving down the group. All right. So if the number of shells increase when we are moving down the group, means electrons are moving away from the nucleus, and obviously the size is going to increase, right? Let's say this is the nucleus. If I am having one shell, this will be the size. Okay. If I am having two shells, of course the size is going to increase. This we can see only. And if I am having three shells, the size will further increase. So when the electrons are getting added to the next shell, because of the addition of another energy level, the atom gets bigger. So down the group, try to understand that atomic size increases generally down the group. So like it will increase from fluorine to chlorine to bromine to iodine, like this. It will increase from beryllium to magnesium to calcium, strontium, barium. Of course exceptions will be there, okay, but this is the general trend. It will increase from lithium, sodium, potassium, rubidium, cesium. All right. So this is how atomic size varies in the periodic table. I hope it is clear. So you just have to remember the reason. All right. Then another kind of radius comes up, that is ionic radius. Till now we were talking about atomic radius. Ionic radius, you know that whenever atom loses or gains an electron, so what happens is ions are formed. Alright, cation is formed, and whenever any atom gains an electron, so anion is formed. Okay. So again we will be measuring the ionic radii in the ionic crystals. So generally the trend is that ionic radii, they exhibit same trend as atomic radii, whatever we have discussed. But just to try to understand that if I compare these three things, okay, if I compare cation, anion and the parent atom, so the size of the cation will be smaller than the parent atom. Okay, why? But now let's say metal atom was sodium. Okay, I have made sodium ion. Let's say this is the case. Now sodium was having 11 electrons. Now when one electron gets removed, sodium is now having 10 electrons, right? So when this sodium has now 10 electrons, the number of protons is same, right? protons is same means the nuclear charge is same. So now those 11 protons are holding on to the 10 electrons. So what does that mean? That means that those protons will be holding those 10 electron more tightly, so that is why the size would decrease. And same thing happens with the anion. The size of anion will be more than the metal atom. Now why? Because let's say if I talk about chlorine, so chlorine will take an electron and become chloride. So chlorine was having 17 electrons, now it has 18 electrons. Okay, now addition of one or more electrons would result in increased repulsion because the electrons are getting added to the same shell, so there would be more repulsion. More repulsion and the nucleus has to hold on to more electrons. So because of repulsion and all of that, there is a decrease in effective nuclear charge. Okay. So try to understand this कि cations will have a lower size than the metal atom and anions have a more size than the metal atom. But let's say if we are having some ions which have same number of electrons, we call them as isoelectronic species. For example, O2 negative, F negative, Na positive and Mg2 positive. Now if they are asking you, all of them have 10 electrons. But if they are asking you that arrange them in the order of ionic radii, then what would be the case? Radii would be different. Why? Because all of them have different nuclear charges. Although electrons are same 10, but all of them have different number of protons, so different nuclear charges. Okay, so cations with greater positive charge will have a smaller radius because of the greater attraction of electrons to the nucleus. Means magnesium 2 positive will have the lowest atomic radii, then sodium, then F negative, and greater the charge on the anion, more will be the radius. So O2 negative means it has gained 2 electrons, and gained 2 electrons means the repulsion would be more. So this is going to be the order. Keep that in mind. Alright. Okay students, next up is ionization enthalpy. Very important. Alright. So what is ionization enthalpy? So you know that it's actually a tendency or measure of tendency of an element to lose electron. So you know कि let's say an atom loses electron. So how much energy is required to remove that electron from the isolated gaseous atom is known as the ionization enthalpy. For example, if I am talking about any element X, so it loses an electron and it becomes X positive. Okay, so how much energy is required? We will be calling it as the first ionization enthalpy. First ionization enthalpy means that the energy required to remove the first electron. Let's say if I am having magnesium will remove first electron, then the second, it becomes Mg2 plus. Now units are kilojoule per mole. Now second ionization enthalpy means this X plus wants to lose one more electron. So this X plus will lose one more electron and it will become X2 positive. Okay, so that will be the second ionization enthalpy. Okay, H2 we can write, H1, H2. So that will be the second ionization enthalpy, and try to understand that always the second ionization enthalpy will be more than the first one. Why? Because it would be difficult to remove the electron from already positively charged ion. Okay, already it is having more nuclear charge. So second ionization enthalpy, so you can say ki IE2 will always be greater than IE1. Same goes with IE3. If IE3 is there, so third ionization enthalpy is also more. Okay, so that is the thing. Now let us see the trend. So how the trend goes. So what happens is that the first ionization enthalpy, or if I am talking about the ionization enthalpy, it generally increases as we go across a period and decreases as we descend in a group. Now why? So when we are moving from lithium to fluorine in the second period, let's say, successive electrons are added to the same shell, right? They are saying same principal quantum level, and shielding of the nuclear charge by inner core electrons does not increase very much. So see, ionization enthalpy again will depend on the effective nuclear charge, and you know that inner electrons shield the outer electrons from the nuclear charge. But since here the electrons are added to the same shell, shielding is not much. Okay, so there is an increased attraction of the electrons to the nucleus, means the effective nuclear charge increases. So we can say that when we move left to right in the period, the ionization enthalpy generally increases. Of course, there are certain exceptions that I will discuss just now, but try to understand this is the general trend I am saying. And now see, when you are moving down the group, atoms are moving away from the nucleus, right? That's what we have done because new shell gets added. So, wouldn't it be easy to remove that outermost electron from the atom, right? So, that is why what happens is when we are moving down the group, the ionization enthalpy decreases because of the increase in atomic size and decrease in effective nuclear charge. Okay. Because shielding also happens because the shell is getting added, so inner electrons are shielding the outer electrons from the nuclear force. So this shielding actually outweighs the increased nuclear charge and outermost electrons, and the removal of that outermost electron requires less energy. This is the reason. Okay, but students, try to understand this thing. So this is actually the chart for the second period elements. Okay, second period elements, that is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Of course, your noble gases will have the highest ionization enthalpy because they are very stable and it is very difficult to remove that electron. So what I have told you that the trend should be ionization enthalpy decreases from lithium, sorry, yeah, just a minute. Ionization enthalpy would increase when we are moving left to right. More energy is required to remove that electron. So the trend should be this. So most of us will think, left to right, it is increasing, right? But you have to keep the electronic configuration in mind as well. Now just see the chart. The trend actually is, so the actual trend is, first, it is increasing from lithium to beryllium, and then beryllium, after beryllium, boron has lower ionization enthalpy than beryllium. So it means boron will come before beryllium, then it's carbon, then after that you can see out of nitrogen and oxygen, oxygen has a lower ionization enthalpy than nitrogen. So oxygen will come before nitrogen and then fluorine and then neon. Okay. So this is the correct trend. So you can see two exceptions here in the behavior of beryllium and boron and nitrogen and oxygen. Now why that is happening? So students, when you are talking about same principal quantum number, you should understand that s electrons are attracted to the nucleus more than the p electron, means penetration effect of s electron to the nucleus is more than a p electron. So write the electronic configuration of beryllium and boron. Okay, so if I am talking about lithium, then beryllium. So beryllium is 1s2, 2s2, and boron is 1s2, 2s2, 2p1. Now if you have to remove the outermost electron from beryllium, you have to remove from 2s orbital, and here you have to remove from 2p orbital. Okay, so penetration of 2s electron of to the nucleus is more than a 2p electron. So means 2p electron is more shielded from the nucleus than the 2s electron. Okay, and moreover it is a fully filled shell or fully filled orbital also. So it is difficult to remove that electron from beryllium as compared to boron, because one, it is present in the 2s orbital, which is more penetrating towards the nucleus, okay, less shielded, whereas 2p electron can be removed more easily than that 2s electron. So that is why it's easy to remove that 2p electron from boron as compared to the removal of 2s electron from beryllium. So that is why boron has smaller first ionization enthalpy than beryllium. Okay, this is the first. Now second anomalous behavior comes in nitrogen and oxygen. Now write the configuration of nitrogen. it is 2s2. I'm not writing 1s, okay? It is 2s2 2p3. If I am drawing 2p3 orbital, so all the electrons go like this according to Hund's rule. And in oxygen, it is 2s2 2p4. So 2p4 you can draw 1, 2, 3 and then 4. Now students, first of all you should know that half filled and fully filled subshells are extra stable. So this 2p3 is more stable than 2p4. Okay, because it is half filled. Why? Because what happens is that here the electrons are in different orbitals. Okay, in oxygen these two electrons are in same orbital, so they have increased electron repulsion. So it is easier for us to remove that electron from oxygen than to remove it from the nitrogen. So that is why the ionization enthalpy or ionization energy of nitrogen becomes more than oxygen. Okay, the reason is that half filled subshells are extra stable. All right, so that is the thing. Now let us, so this is the trend for second period, and this question was asked in NEET examination also. They gave carbon, nitrogen, oxygen, fluorine, and you have to give the trend. So if you don't know this anomaly, you might get this question wrong. So try to understand this. Now let us talk about the electron gain enthalpy. So just like we require energy to remove the electron, so what happens is when an atom gains an electron to convert into negative ion, so the enthalpy change accompanied in that case is the electron gain enthalpy. Okay, so means it tells us about the ease with which an atom gets added to an by which the atom adds an electron to form a negative ion. So it can be endothermic or exothermic also. Okay, so when you are adding electron, energy can be released also, energy can be absorbed also. Okay, mostly for many elements energy is released when electron is added because they become stable, just like the halogens group 17 elements. They just require one electron to become stable. So when they gain that one electron, okay, large amount of energy is released. All right, so it means, and when energy is released, you know delta H is negative. We have studied thermodynamics and all of that as of now, right? So in that case, the electron gain enthalpy are highly negative. Highly negative means large amount of energies are released, because just by picking up one electron, they attain the stable noble gas configuration. Okay. Noble gases, if I am talking about noble gases, now noble gases are already stable. If you want to add electron to a noble gas, you need to provide a lot of energy. Okay, so that's why noble gases will have large positive electron gain enthalpy. Okay, because now they are going from stability to instability. So that is the case. So in electron gain enthalpy, you know, generally we don't have such a trend because there are a lot of exceptions from atom to atom. But try to understand that towards the right, upper right of the periodic table, before the noble gases, the electron gains enthalpy are very like they have large negative values, like for halogens, for group 16, because they gain electron and they become stable. Okay, so we can say that electron gain enthalpy becomes more negative with increase in atomic number across a period. When we are moving left to right, the electron gain enthalpy is becoming more negative. Okay, because effective nuclear charge is increasing from left to right, and it will be easier for us to add an electron to a smaller atom, okay, than to a positive charge nucleus. All right, is it clear? Now down the group. So down the group, the electron gain enthalpy will become less negative because size of the atom is increasing and the added electron will be farther from the nucleus. Okay, so that is why when we are moving down the group, electron gain enthalpy becomes lesser negative. Less energy would be released. Try to understand. Okay. But again there is an anomaly in the second and the third period elements. All right, that we will see, or you can say when we are moving from oxygen to fluorine, second period mein, the electron gain enthalpy of oxygen or fluorine is less negative than that of the succeeding element, means the third period. Why? So this is an anomalous case. You should know for second, although hona kya chahiye, what should be the case, that when we are moving downwards, the electron gain enthalpy becomes less negative. So the electron gain enthalpy of third period element should be less negative than the second period. But what happens is that in the case of oxygen and fluorine, they have less negative electron gain enthalpy as compared to the next element, that is sulfur or chlorine, because in the case of oxygen and fluorine, the incoming electron goes to the second shell, and second shell is smaller. Okay, so there are more electron repulsions. Okay, but in the case of sulfur or chlorine, the electron goes to the third shell. It occupies a larger region of space and electron repulsion is less. So this question can also be asked if I am talking of halogens only, fluorine, chlorine, bromine, iodine. So this electron gain enthalpy decreases or becomes less negative. But the trend is that chlorine will be having less negative. Okay, so that is the case. यहाँ पर chlorine and fluorine में there will be an anomalous behavior. So chlorine will be having the highest electron gain enthalpy, more than fluorine also. Okay. Next is electronactivity. So you know electronactivity, it is not a measurable quantity, but it is measured on a scale. So it's actually a ability of an atom to attract the shared pair of electron towards itself. So a number of scales were given by scientists: Pauling scale, Mulliken scale, Alred-Roschow scale. Okay, so the widely used is your Pauling scale, which actually assigned a value of 4.0 to fluorine, which is the most electronegative element of the periodic table. So you know, when you are moving left to right in the periodic table, nuclear charge increases. So means atom will have more tendency to attract the shared pair of electrons. So in that case, electronegativisty generally, we are saying generally, increases from left to right in the period. And when we are moving down the group, because nuclear charge decreases, size of atom increases, the electronegativity decreases down the group. Okay. The reason I have already told you, attraction between the outer electrons and nucleus increases as the atomic size decreases. Okay. That is why electronegativity increases left to right. So this trend we can use to tell the non-metallic and metallic behavior. So non-metallic elements, you know, they have a strong tendency to gain electrons. So electronegativisty is directly related to the non-metallic properties. So, and it is inversely related to metallic properties. So on the left hand side of the periodic table, the electronegativity is less. So the metallic nature of the or metallic character of the atom would be more. Okay, so we can say is that when we are moving left right in the periodic table, non-metallic character increases, and when we are moving top to bottom, metallic properties increases. Okay, down the group, decrease in non-metallic behavior or increase in metallic property. So this is the chart. This is the chart that you can see, students, and general chart for telling the different properties that we have just discussed. Okay, so this is the trend. You have to keep in mind the trends what we have discussed, but you have to keep in mind the anomalous behaviors as well. All right. So that's it from this chapter. We will see you in the next chapter. So until then, if you are having any issues or any doubts, you can let us know through the comment section. You can ask us. All right, students. So thank you so much.